Consider a light source having a wavelength with intermediate energy, such as an X-ray source. And this light source is incident on a sample, such as graphite. So in this case, because the energy of the light source is a lot higher than the work function to eject an electron, then the electron can basically be treated as a free electron. So this is in contrast to the photoelectric effect, where the light source is ultraviolet radiation, which is considered low energy. So therefore, in the photoelectric effect, an electron absorbs a photon, but with the Compton effect, the free electron cannot absorb a photon. So therefore the photon gets deflected, like in a particle collision. And a deflected light particle, or photon, has a wavelength that's greater than the wavelength of the light source. So the deflected photon has lower energy. So here we have a detector to capture photons that are deflected at different angles. And these angles are from 0 to 180 degrees. So for the different angles here, we have a plot of intensity versus the wavelength that's captured at the detector. So in the case where the angle is 0 degrees, which is this case, then you only get one peak wavelength, being equal to the wavelength of the incident light. And in this case, for example, where the detector is at 45 degrees from the path of the incident light source, so you'll see two peaks, where we have the wavelength of the incident light source and the wavelength of the deflected light source, being the two peaks. So the deflected photon has lower energy, and therefore the deflected wavelength is larger than the incident wavelength in this case. So this here is known as the Compton Shift. And in this case, if you have the detector at 90 degrees, then you'll still have two peaks, but the deflected wavelength is even larger than the incident wavelength. So therefore the Compton Shift is larger with an increase in angle. And note that at the detector, discrete wavelengths of light are recorded. So the data for intensity versus wavelength looks something like this, for example. And these curves fit through the data. So the main idea is that in Compton scattering, a photon interacts with a free electron, and the Compton effect is where the photon that emerges from the interaction has a lower energy and therefore a longer wavelength than the incoming photon. And the magnitude of the Compton shift is related to the direction of the photon after the collision. Compton scattering, which we saw in the previous experiment, which is also known as the Compton effect, is further evidence that light is a collection of discrete quantized energy packets called photons. So the particle nature of light was demonstrated in a photoelectric effect and further backed up by the observation of Compton scattering. Now Compton scattering can be explained by treating a photon as a particle and applying the conservation of energy and conservation of momentum to the collision between the photon and the electron. So before the collision, we have this configuration, and after the collision, the photon and the electron fly off in different directions. So here we have the momentum of the electron going in this direction, and we'll take the angle to the horizontal as theta e, and this angle between a deflected photon and the horizontal as theta p. So that's before and after the collision. So essentially, the transfer of the photon's energy to an electron results in the energy, momentum, frequency, and wavelength of the photon changing. And recall the relationship between energy and frequency of light, and also the de Broglie wavelength, which was equal to Planck's constant on the momentum of a particle. And now if we apply a conservation of momentum in the horizontal direction, we have the initial momentum of the photon is equal to the final momentum of the photon by cosine theta p plus the final momentum of the electron cosine theta e. And doing the same in the vertical direction, both the photon and the electron don't have momentum in the vertical direction initially, and we have the final momentum of the photon sine theta p minus the final momentum of the electron. So these fly off at different directions, and that's multiplied by sine theta e. And similarly, if you apply conservation of energy, we have the initial energy of the photon plus the rest mass energy of the electron. So the rest mass energy is stored inside a stationary particle as a result of its mass. So that initial energy is equal to the final energy, being the final energy of the photon, plus the kinetic energy of the electron, plus the rest mass energy of the electron. So note that we can write these different relationships. So for example, for a photon, you have the speed of light is equal to the wavelength by the frequency of light. And that allows us to write this relationship in terms of wavelength. And you can also use the relativistic energy momentum relationship, which is beyond the scope of this introductory physics course, and do some algebra, and you'll come up with the following relationship. So you have the Compton shift. So remember that's the difference between a deflected wavelength and the incident wavelength from the experiment. And that's equal to Planck's constant by the mass of the electron by the speed of light by 1 minus cosine of the deflected angle. So the change in wavelength experienced by a photon after colliding with an electron is related to how much the photon's direction changes. So if you make some substitutions, Planck's constant was 6.626 by 10 to the minus 34 joule seconds, and the mass of an electron is 9.109 by 10 to the minus 31 kilograms, and the speed of light was 2.998 by 10 to the 8 meters per second. And if you evaluate this expression, which we'll call the Compton wavelength, you get lambda c is 2.426 by 10 to the minus 12 meters. Let me just make a bit of room here. So essentially the Compton wavelength is 0.00243 nanometers. If you multiply this by 10 to the 9, or 2.43 picometers. So the Compton shift is quite small, and it gets larger with angle. So this here is where the photon does not get deflected, and this here is where the direction of the deflected photon is 90 degrees from the incident direction, and this one is at 45 degrees. So as we can see, the Compton shift increases with an increase in angle. So for an angle of 0, cosine theta is 1, so there's no Compton shift. For an angle of 45 degrees, you get 1 minus 1 on root 2. And for an angle of 90 degrees, cosine theta is 0, and the Compton shift in this case is equal to the Compton wavelength. And if you increase the angle to 180 degrees, so cosine pi is minus 1. So in that case, the Compton shift is equal to twice the Compton wavelength, which is the maximum shift that can occur. An 80 picometer X-ray is incident on a graphite target, and we're asked to find the wavelength of the X-ray scattered at an angle of 45 degrees, and the largest and smallest Compton shifts. And we're given the Compton wavelength. So the Compton shift is equal to the Compton wavelength, and we'll use picometers here, in accordance with the problem, by 1 minus cosine of the scattering angle. So on the left hand side, we have the scattered or deflected wavelength minus the incident wavelength. So that's equal to 2.43 picometers by 1 minus cosine 45 degrees. So solving this equation, we get the scattered wavelength as 80.7 picometers. Now the largest Compton shift occurs when theta is 180 degrees or pi radians. So therefore the largest Compton shift is 1 minus negative 1, which is 2, multiplied by the Compton wavelength. So that gives 4.9 picometers. And the smallest possible Compton shift occurs when theta is 0 degrees. So therefore the smallest Compton shift that's possible is 0 picometers.